probably whatever day we have that quiz, I may want to see the homeworks leading up to that quiz. Okay? Other questions, issues, concerns? Okay. All right. So if you've had honors pre-calc, or if you're in certain physics courses, you may have already talked about the concept of the derivative. Okay? You don't need to have any knowledge at this point of the concept of the derivative because we are introducing that today. We're going to talk about where the derivative comes from, what it really represents. There are a lot of shortcut techniques to find derivative functions, but all of those shortcut techniques come back to one basic concept of the derivative. And the derivative is, in fact, a limit. Hence the reason we do limits first. Okay. Before we talk about a derivative, which is an instantaneous rate of change, we're going to talk about an average rate of change. Okay? Any kind of rate of change, or the change between 2 points in time, which is typically what we're talking about when we talk about an average rate of change, we talk about that a lot of different places. Anytime we talk about something increasing or decreasing, we're talking about a rate of change. Every time in Algebra 1 you measure the slope, you were talking about a rate of change. Anytime you're talking about meters per second or feet per hour or dollars per hour, those are all rates of change. Tons and tons and tons and tons of applications in the world dealing with rates of change. A rate of change, an average rate of change, is a slope. Okay? It's the slope of the line that would connect 2 points. We're going to see the letters AROC for average rate of change. Okay. And what I want you to think, or what you can think, A for average rate of change, and our average rate of change is essentially an algebra slope. And if you think back to algebra, a slope is a change in y over a change in x. y2 minus y1 over x2 minus x1, our super great friend, the slope. Okay? Slope between 2 points, cornerstone of Algebra 1, writing the equation of a line, knowing its slope, measuring the slope from 2 points, measuring the slope from the graph, counting rise over run, whatever different things we did with it, slope, 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 slope. Okay? In calculus, how we're going to differentiate between a couple different kinds of slope or rates of change is we're going to talk about average rate of change versus instantaneous rate of change. And we'll write that down in a minute, so you don't have to worry about writing it down now. An average rate of change is an algebra slope. When we measure the slope of a line that connects 2 points, that line is called a secant line. Okay, so I have 2 points on a graph. I connect those 2 points on the graph with a line. I measure the slope of that line. That's called the secant line, and the slope of that secant line is the average rate of change. 90% of the problems in calculus have to do with trying to figure out what the heck they want you to do. Okay? We have a bunch of skills that we're going to learn, but if we don't know when to do what skills, we're kind of stuck. So, seeing those words, find the average rate of change for the function y equals x squared minus 3 over the interval 2, 3 is telling us let's take 2 points on this function, the point where x equals 2 and the point where x equals 3. Okay, one thing to remember in an interval like this is an interval of x values. Okay, so if I'm looking at an x of 2, y would be 1. You with me? All right, maybe. If x is 3, what is y? 6. Because I'm using this, right? That is the function that relates x and y. Okay. And so the average rate of change would be, this is just me, I would do 6 minus 1 and then 3 minus 2. You can absolutely do 1 minus 6 and then 2 minus 3. You just have to be careful of your order, that you're consistent with your order. And so the average rate of change would be 5. Let me throw a page in here for a second. Okay, so what that means is, you know, or what we can say what we just did is, this parabola we were talking about, x squared minus 3, if I'm at the point 2, 1, and then I'm at the point 3, 6, when I connect those 2 points, the slope of that line is 5. Not a very good picture, but I think you get what I mean. Okay, the slope, the rise over run change, oops, that's horrible. You know, if I was going from this point on that function to this point on the function, it's an increase of 5 units up for 1 unit over. All right, questions? We will ask you average rate of change questions in calculus. It is possible you will see that phrase. You will be asked to find those. And now here's another one. Let's see what you can do with this one. Find the average rate of change of that function, the ln of x minus 2, on the interval from 1 to e. Okay. All right, so what do we need to do first? Do what with 1? Plug it in, okay. So f of 1, the natural log of 1 minus 2. Yeah, if you didn't do your summer packet, so you didn't review E and natural log, guess what? We want to do that. Same thing with the trig stuff. All that stuff is sitting in the summer packet that you can go back, and if you can't, I don't know if it's still on the website actually now that I think about that. I'll post it on Schoology if you're not able to get it. Let me double check that, okay? But the understanding is you're sitting in this class with some pre-calc knowledge. The natural log of 1 is 0. And so one of my ordered pairs is 1, negative 2. F of E, the natural log of E minus 2. The natural log of E is 1. So my point would be E, negative 1. So my average rate of change, kind of squeeze it over here, about negative 1 minus negative 2 over E minus 1 So 1 over e minus 1. What a fun answer. Oops. No, I don't want to close for any. Cancel. Okay. Y minus y. Actually, and x minus x. Negative 1. Actually, I did negative 1 minus negative 2. So I did e minus 1. If you prefer, and I'll scoot this one right here, if you do negative 2 minus negative 1 over 1 minus e, another potential answer would be negative 1 over 1 minus e. That is equivalent to 1 over e minus 1. It's just the opposite. I mean, both numerator and denominator are opposite, so these are actually equivalent. Positive 1, e minus 1, negative 1 over 1 minus e, same numeric value. Questions. So when I throw an average rate of change at you, you're like, okay, it's a slope. It's an algebra slope. An average rate of change is an algebra slope. I know it feels sometimes because we're saying the word average, you feel like you should be finding like lots of slopes and adding them together. Okay. But that's not what we're talking about. Now, 2 points on the curve connected make a secant line. What we're going to do now is we're going to take the 2 points that are making the secant line and we're going to move them closer and closer together so that the secant line becomes closer and closer to a tangent line. We're basically going to go from the idea that, hey, if I have 2 points on the curve, I can get a slope or an average rate of change. But if I take and I move the 2 points really close together, closer and closer and closer and closer together, the line that connects them instead of being a slope through 2 points, it essentially becomes what is a slope that you can calculate at a single point. And that is what we're going to refer to as our instantaneous rate of change. Okay. How are things changing at one point? Not between this point and this point, but at a single point. Slope at a single point. y2 minus y1, x2 minus x1, but the 2 points get closer and closer together. Now, I always forget to do this. Did I find demo? Let me find this if I got that. Looking for the demo. Okay, this isn't a bad demo. I'll kind of keep this handy. Okay. So here's the geometry of what we're going to do. Okay. And I'm going to just kind of show it. So let me figure out if I can get something not showing. That's the green guy. Yeah, okay. This is kind of a built-in. So looking at the green kind of curvy function, I've got 2 points on that green curvy function, and I've got a red line, which is a secant line, connecting those 2 points. That's a normal average rate of change calculation, the slope between this point and this point. What happens as we move one of the points closer to the other is you start to get a single line that actually matches up with this other, you don't understand why that other line is there. So actually, I kind of don't want that other line there. Can I turn it off? If I take that out. Yeah, that's okay. Okay. So here's what we're going to be doing. We're going to take 2 points on a curve, and we're going to take one of the points and move it closer and closer and closer to the other point so that the slope between 2 points, or the line between 2 points, becomes a line that essentially touches the curve at a single point. Now this isn't letting me put one point right on top of the other, but this is the idea here, is that this is what we're going to do mathematically, is we're going to take the difference between, we're going to take this slope between 2 points, and we're going to convert it so that we're essentially finding the slope between at a single point, so that those 2 points are super close together. And that's going to be the idea. And this is what's showing it in a non-fun way. Okay, so here's how we're going to do that. We're going to take our curve, and our curve has 2 points on it, point P and point Q. The name of our curve is f of x. So if point P has x for its x coordinate, I can write its y coordinate as f of x. So that's just a way to write the coordinates of point P. Make this a lot bigger. There we go. Oops, maybe a little smaller than that. And how I'm going to talk about point Q, instead of giving point Q its own coordinates, I'm going to measure point Q in relation to point P. So I'm going to take the coordinates of point P and I'm going to add a little bit onto it. I'm going to say point P plus a little bit, the x from point P plus a little bit gives me the x for point Q. And that delta x is going to represent a little bit, a small amount. So we have an x at point P, and we have the x at point Q, which is x, the x from point P plus a little bit, which then makes the y on point Q f of the x from point Q. So this is like an x1. That is essentially y1. This is x2, and this is y2. They look super scary, but they're just ways to represent 2 distinct points on the curve, but relate them to each other. Yes, question? Yeah, sure. So I have the point P that I said, okay, we're going to say it's got a coordinate, an x coordinate x. So I would write its y as f of x. Okay, does that make sense? So then point Q, if I talk about the coordinates of point Q and I say, all right, point Q's x is a little bit more than point P's, I'll write it like that. The x from point P plus a little bit, that's what that delta x is. It represents just a little bit more. And so if that's the new x on point Q, the new y on point Q is f of that crazy looking x. Yeah? No?
Are we going to have like subscripts on these types of equations?
We can, yeah. No? Yes? No? Yeah. Okay, so instead of me taking and going, hey, I'm going to call this AB, and I'm going to call this one CD. So there's kind of no relationship between any of them. They're just four random things. I'll say, well, if I call this one A, his Y is F of A. So they're connected. Okay? And then if I say this one is A plus a little bit. Okay? No? I'm going to talk, because whatever this, if this is 2, and I add a little bit, and this one has an x of like 2.5. Or if this is like 7, this is like 7.2. So with whatever A is plus a little bit, and then this is F of that. Yeah? Okay. We're gonna have to go with it. You might not know why I'm doing that, but you have to accept that this is a way I can talk about these points in that way. So if I was going to do that, the slope of PQ would look like this. If I want to take y2 minus y1 and x2 minus x1, but I want to use like my fun names. Okay. Everybody hang in there. We're going to get there. F of x plus delta x minus f of x. Okay, where did those come from? They're the y's of the points. The y's of these points I wrote with these. The p points y was f of x, and the q points y was f of x plus delta x. So this is just a y. This is y2, and this is y1. X2 minus x1. You can write parentheses around it. You don't necessarily need it, but you can. You don't need it. All right. So let's back it up. I just wrote a slope, just like algebra 1 all day long, y2 minus y1, x2 minus x1. I just used some weird notation to talk about the coordinates of point P and the coordinates of point Q. Okay. And there is a reason I did that we're going to show you in a minute. How are we? Yes, Gloria. What's delta y? Well, delta y is just represents that this is a change in, this little bit is change in x, this little bit is change in y. It's just marking it, but it's actually not something we're going to plug into the formula. Okay? But this is just saying, hey, the difference between the x here and the x here, we could mark with delta x. And if we wanted to describe the difference between this y and this y, we could do it with delta y. All right. So we wrote a slope. A scary looking slope. And now I'm going to clean it up a little bit. My denominator, I have x plus delta x minus x. So my denominator can just simplify to delta x. That's just algebra. Whoops, that's not a good idea. There we go. That's delta x. So this is f of x plus delta x minus f of x all divided by delta x. Okay. Now, that's the slope between the 2 points. That's the slope between points P and Q. I want P and Q to essentially get really close together. I want to move Q super, super close to P so that the distance, the space between them is almost nothing. So that this little bit of difference between them is super teeny tiny, like almost zero. And I'm going to represent that with a limit. Okay. If I take the limit as delta x approaches 0 for this structure, for a function x, this function, this limit, is going to calculate the instantaneous rate of change, or otherwise known as the derivative, of f of x. Right. The derivative of a function can get measured by a limit. If we take a function and we set this limit up for the function, the result of the calculation of this limit is going to be the value of the derivative. All those other things you may have learned shortcuts back in the back of your head from pre-calc honors or other friends who are in BC or whatever, those are all derivatives. But the reason all of those can happen is because of this. And as of right now, this is how we calculate derivative values. When I say to you, we're going to use the limit definition to find the derivative value, that means we're using this. We're not using a shortcut.
Would the derivative be the same no matter where we get those 2 points from on the curve?
No. The value of, okay, so yes and no. There is a function that can represent that derivative that can be generic. The actual value of the derivative would be different depending on where you put those 2 points. Okay? Okay, so quick summary here. Average rate of change is f of b minus f of a over b minus a. Instantaneous rate of change, specifically at x equals a, means, for f of x, means we're going to do the limit as delta x approaches 0 of f of a plus delta x minus f of a all over delta x. These are our calculation tools. The average rate of change calculation, the instantaneous rate of change calculation, average rate of change, slope, algebra 1 slope, everybody loves it, y2 minus y1 over x2 minus x1. Instantaneous rate of change is a derivative, and for all you know, the only way to get a derivative is to use a limit. Until Newton and Leibniz recognize a bunch of shortcuts and tell us what those shortcuts are, and then we can use the shortcuts, we're calculating our derivative values using limits. Okay. Now, you don't ever have to explain to me where this came from, but you have to know it and be able to use it. So you have to know that the instantaneous rate of change, or the derivative of f of x at x of a, can be measured with this function. And we are going to practice now doing exactly that. Finding the instantaneous rate of change, or the derivative of a function at a particular value using this limit. You need this formula memorized. You actually need two of them memorized. Let's go to the next page. Now, to make it a little nicer, some more modern notation replaces delta x with the letter h. Okay? So you'll see this as h approaches 0 as opposed to as delta x approaches 0. Once again, I've marked for you one more time that this is also called the instantaneous rate of change. It's called the derivative. It is notated with that notation, or multiple different notations, but that's one notation to say I want the derivative of f, or the instantaneous rate of change of f at x equals a. If you can calculate the limit, then the value of this limit is that derivative. Okay. All right. So here we go. We're going to calculate our first derivative using a limit. This is our function. A is 3. So I need f of 3, first of all, which appears to be 39. Sorry. Okay, so 3 squared plus 10 equals 39. Okay. So now I'm going to create my limit. The limit as h approaches 0, actually, maybe I'll do this first. Let me write out what f of 3 plus h will look like, because that's going to be important. We're going to need that. F of 3 is comfortable for us. F of 3 means I take the f function and I plug in 3. 3 squared plus 10 times 3. F of 3 plus h means I do the same thing. It's 3 plus h, quantity squared, plus 10 times 3 plus h. Okay. That's function notation, function arithmetic, I don't know what you want to call it, working with a function. F of 3 plus h means take 3 plus h and plug it in the f function. So I needed f of a, or f of 3, got it. I need f of 3 plus h, got it. Oops, crazy wheel. All right. So now I'm going to write out my limit. It might be a good idea to write the formula first. The more you write the formula, the more you'll memorize it. So limit is h approaches 0, f of a plus h minus f of a all divided by h. So in this problem, that's 3 plus h all squared plus 10 times 3 plus h. All that together, minus 39. All divided by h. Okay. All right, deep breaths. Process that. You may not know where this is going, and that's totally fine. You're not supposed to. All I'm asking from you right now is to be able to follow what I'm doing. Following doesn't mean that you're confident that you can do it yourself, but I need you to make sure you're following, not just copying, but understanding what I'm writing down. Everything here in these brackets is that part. F of 3 plus h, or f of a plus h. In this problem, a is 3. Everything in this bracket, that 39, came from here. You with me? Sorta?
Yeah.
Maybe? Yes.
Why didn't we expand it up?
I just didn't do it yet. I'm not done yet. I'm going to expand next. If you prefer to expand ahead of time, you can. You know, so if you want to expand this out first before you plug it in, go ahead. I tend to not. I tend to write it in there and then I start doing my work. Other questions? No? Okay. So, as indicated, well, let's talk about this limit actually for a minute. If I try to calculate this limit and I put a 0 in for h, actually let me take it off of here for a minute. You, dual this lady off. What happens if I try to calculate this limit?
It doesn't exist.
Why?
Because h is in the denominator.
You get 0 in the denominator, so this is a DNE limit. We're done. What about the top?
You get h squared plus 10h.
As h approaches 0, what happens to the top?
Zero.
This is a 0 over 0. That's why we learned about that. Because every time we try to do the limit definition of the derivative, guess what? It's 0 over 0. Every time. Every time. Kind of go like that because it's gangster. Every time. Every time we want to do a limit definition to get a derivative, it's going to be 0 over 0. We can't get away from it. We're going to have to apply our magic techniques to these limits to calculate them. All right, so magic technique number 1, expanding. Rewriting this using algebra. So how about the limit as h approaches 0 of 9 plus 6h plus h squared. Okay, that's 3 plus h, quantity squared. Plus 30 plus 10h minus 39 all divided by h. So the 30 plus 10h is the 10 times 3 plus h. Oh, yeah, 10 times 3 plus h. Make sure I had that. All right. Are you with me? All right. Here we go. I'm going to go looking for like terms. Constants. 9 and 30. 9 plus 30 minus 39. Adds out to 0. Makes me happy. 6h. 10h. 16h. h squared. Nothing to put with that. All divided by h. Still 0 over 0. But I can factor out an h. 16 plus h factored out, so h times 16 plus h, all divided by h. Those will divide. Oops, this is the limit. So this is the limit as h approaches 0 of 16 plus h. Final answer, 16.
Are they always going to be able to factor out like that?
Not all of them are pretty. There are some that are more complicated, but the few that we're going to do using the limit definition, we should be able to, through some algebra, either factoring or expanding or factoring or conjugate multiplication or common denominator, the algebra tricks we've kind of learned, we should be able to get ourselves to a numeric answer, yes. Okay. All right, let me turn that off for a second. Okay, and let me zoom that down for a second. So, once we set up this problem, the new part for this unit is technically over because everything that happened after that was limit calculation or algebra. 3 plus h quantity squared, expanding that out. Writing that, combining those terms, factoring out the h. All of that is the past unit, unit 1. There are lots of function combinations that when you apply the limit definition of the derivative to them, you've got to know some pretty sophisticated tricks to get the limit to work. The good news is, that's always what I say, the good news is we're not going to do that many limit problems like this. We're going to do a few, but then we're going to go back to what Newton and Leibniz figured out is after they did a bunch of limit problems with different kinds of functions, they figured out, oh, there's shortcuts. There are ways to get around this definition. This definition leads to certain patterns of behavior, and we can use those to our advantage. Okay, questions at this point? Probably the biggest question is when you look at that, you're like, could I do that myself? Right? Not yet. But let's try another one. So let's go to find yourself a clean little space or a separate sheet of paper. Let's say f of x. Here we go. Okay. Okay. Let's give it a shot. Find me the instantaneous rate of change of f of x at x equals -1. Otherwise known, I'm going to write this a couple different ways. The derivative of f of x at x equals -1, f prime of -1. I'm going to stop this for a second.